Welcome back to Chapter 11, Differential Calculus, Section 11.1, Limits, a strategy for finding limits.
Now let's look at a strategy for finding limits. This strategy deals with functions that agree at all but one point. So Theorem 1.7 says, let C be a real number and let f of x equal g of x for all x not equal to c and an open interval containing c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists, and the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. Now let's apply Theorem 1.7. For example 7, we're asked to find the limit as x approaches 1 of x cubed minus 1 divided by x minus 1. So we let f of x equal x cubed minus 1 over x minus 1. Then what we want to do is fully factor the numerator and denominator and then divide out common factors. So f of x then equals x minus 1 times x squared plus x plus 1 over, the denominator is already factored, so over x minus 1. And that equals x squared plus x plus 1, which equals g of x when x is not equal to 1. Now notice that g of x is a polynomial, and polynomials have domains of all real numbers. Therefore, g of x is defined at x equals 1, and the limit as x approaches 1 of g of x does exist. Therefore, we can apply Theorem 1.7 to conclude that f of x and g of x have the same limit at x equals 1. And so the limit as x approaches 1 of x cubed minus 1 over x minus 1 equals the limit as x approaches 1 of x minus 1 times x squared plus x plus 1 over x minus 1 and then we can cancel out the common factors. That equals the limit as x approaches 1 of x squared plus x plus 1, and by direct substitution that equals 1 squared plus 1 plus 1, which equals 3. And so we can see by looking at the graphs of f of x and g of x that they agree at all but one point x equals 1. And so we're able to apply Theorem 1.7 and say that the limit as x approaches 1 of f of x is equal to the limit as x approaches 1 of g of x, which is equal to 3. Now it's your turn to practice using Theorem 1.7. I would like you to please pause the video and find the limit as x approaches -1 of x squared plus x over x squared minus x minus 2, and then unpause the video and see if your limit matches the limit that I have in my solution. Okay, so we have the limit as x approaches -1 of x squared plus x over x squared minus x minus 2. So we let f of x equal x squared plus x over x squared minus x minus 2, and then we fully factor the numerator and the denominator. We cross out any common factors, which in this case is x plus 1 on the top and the bottom, and we're left with x over x minus 2 equal to g of x when x is not equal to -1. And we notice that the only place that g of x is not continuous is at x equals 2. But we're not concerned with x equals 2. We want to know the limit as x approaches -1. So we can go ahead and apply Theorem 1.7, and we can say that the limit as x approaches -1 of f of x is equal to the limit as x approaches -1 of g of x. So the limit as x approaches -1 of x squared plus x over x squared minus x minus 2 is equal to the limit as x approaches -1 of x over x minus 2, which by direct substitution we find to be 1/3. Now we can look to the graphs on the right to further validate our solution. Notice on the top graph of f of x that at x equals -1, there's a removable discontinuity where the point -1 1/3 would have been. But if you look below at the graph of g of x, at x equals -1, there's actually a point in that same location. So f of x and g of x agree at all but one point. Therefore, we're able to use Theorem 1.7 to find the limit as x approaches -1 of f of x. Now let's just look real briefly at a summary of some of the strategies that we've seen so far for finding limits. We've seen first that we can learn to recognize which limits can be evaluated by direct substitution. And those limits are listed in Theorems 1.1 through 1.6. Second, when the limit of f of x as x approaches c cannot be evaluated by direct substitution, try to find a function g that agrees with f for all x other than x equals c. Choose g such that the limit of g of x can be evaluated by direct substitution. Then, apply Theorem 1.7 to conclude analytically that the limit as x approaches c of f of x equals the limit as x approaches c of g of x equals g of c. And third, use a graph or table to reinforce your conclusion. Now we're going to look at another strategy, the dividing out technique. One procedure for finding a limit analytically is the dividing out technique. This technique involves dividing out common factors. Now let's practice the dividing out technique using example 8. We are asked to find the limit as x approaches -3 of x squared plus x minus 6 over x plus 3. Now we can try to use direct substitution, but let's see what we get. So it's going to be -3 squared plus -3 minus 6 over -3 plus 3. When we simplify that, we're going to get on the top 9 minus 3, which is 6, minus 6 is 0. And on the bottom, we're going to get -3 plus 3, which is 0. And we've learned that since this is a rational function, in order to use direct substitution, -3 must be in the domain of our function, but it's not. So we're going to have to figure out some other way to find the limit. And so we have f of x equals x squared plus x plus minus 6 divided by x plus 3 equals, when we factor the top, we get x plus 3 times x minus 2 over x plus 3. And then we can cross out common factors on the top. So we cross out the x plus 3. And we're left with x minus 2 which is equal to g of x whenever x is not equal to negative 3. So notice that f of x and g of x agree at all but one point. Therefore, we can apply theorem 1.7 and we can say that the limit as x approaches negative 3 of f of x is equal to the limit as x approaches negative 3 of g of x is equal to g of negative 3. So let's go ahead and do that. So we have the limit as x approaches negative 3 of f of x which is x squared plus x minus 6 over x plus 3 is equal to the limit as x approaches negative 3 of g of x which is x minus 2 and that is equal to g of negative 3, which is, by direct substitution, negative 3 minus 2, which equals negative 5. So notice here in the graph we have pictured f of x, which has a removable discontinuity at x equals negative 3, where the point negative 3, negative 5 would have been. The graph of g of x coincides with the graph of f of x, except for g of x equals negative 3 is defined, so the hole would be filled in for g of x. So f of x and g of x agree at all but one point. Therefore, we're able to use theorem 1.7 to find the limit as x approaches negative 3 of f of x. Now it's your turn to practice the dividing out technique. You're asked to find the limit as x approaches negative 2 of 3x squared plus 5x minus 2 over x plus 2. Please pause the video and work the problem. Then once you get your limit, unpause the video and see if you come up with the same solution as I do. So we have here the limit as x approaches negative 2 of 3x squared plus 5x minus 2 over x plus 2. When we try direct substitution of x equals negative 2, we end up with a 0 in both the numerator and the denominator. What this means is that both the numerator and denominator have a factor of x plus 2. So now we can use our dividing out technique. We let f of x equal 3x squared plus 5x minus 2 over x plus 2, and then we factor the numerator and cancel out the common factors. This equals 3x minus 1, which equals g of x whenever x is not equal to negative 2. Since f of x equals g of x when x is not equal to negative 2, we can apply theorem 1.7 and say that the limit as x approaches negative 2 of f of x is equal to the limit as x approaches negative 2 of g of x is equal to g of negative 2. And so we have the limit as x approaches negative 2 of 3x squared plus 5x minus 2 over x plus 2 is equal to the limit as x approaches negative 2 of 3x minus 1, which by direct substitution equals negative 7. F of x is shown in the graph on the left. Notice that there is a removable discontinuity at x equals negative 2, where the point -2, -7 would be. Now g of x would be this exact line, but without the hole in it. So we can see here in the graph that f of x equals g of x, except at one point. Therefore, we can use theorem 1.7 to find the limit as x approaches -2 of f of x. One more thing to mention about the dividing out technique. In example 7, direct substitution produced the meaningless fractional form 0 over 0. An expression such as 0 over 0 is called an indeterminate form because you cannot, from the form alone, determine the limit. When you try to evaluate a limit and encounter this form, remember that you must rewrite the fraction so that the new denominator does not have 0 as its limit. One way to do this is to divide out common factors. Another way to find a limit analytically is the rationalizing technique, which involves rationalizing either the numerator or the denominator of a fractional expression. We know that rationalizing the numerator or denominator means multiplying the numerator and denominator by the conjugate of the numerator or denominator. For instance, to rationalize the numerator of, we have the square root of x plus 4 over x, we multiply the numerator and denominator by the conjugate of square root of x plus 4, which is the square root of x minus 4. And so you can see the work here to do that. So we start out with the square root of x plus 4 over x, and we end up with x minus 16 over x times the square root of x minus 4. So if you're looking for the limit as x approaches 0, you no longer have x alone on the bottom to where when you plug in, you'll get just 0. Now you have x times the square root of x minus 4, so you won't end up with 0 on the bottom. So let's practice using the rationalizing technique here in example 9. Here we're asked to find the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. If we use direct substitution, we'll get the square root of 0 plus 1 minus 1 over 0. We end up with 0 over 0, which is the indeterminate form. So we know that we need to use some type of algebraic approach to get 0 out of the denominator. So in this case, we're going to rationalize the numerator to do that. So we have the limit as x approaches 0 of the square root of x plus 1 minus 1 over x is equal to the limit as x approaches 0 of square root of x plus 1 minus 1 over x times the square root of x plus 1 plus 1 over the square root of x plus 1 plus 1. This equals the limit as x approaches 0. So we're going to distribute the numerator. So we have the square root of x plus 1 times the square root of x plus 1. That's just the square root of x plus 1 squared, which when simplified is just x plus 1. And then we're going to do the square root of x plus 1 times 1, which is just the square root of x plus 1. And then we're going to do negative 1 times the square root of x plus 1. So that's minus square root of x plus 1. And then we have negative 1 times 1, which is just negative 1. And then on the bottom, we can just leave this as x times the square root of x plus 1 plus 1. Now notice that the radical terms on the top cancel, and this will always be true if you're multiplying by the conjugate. Those middle terms cancel. Also, we have a plus 1 and a minus 1 that cancel. And then we're left with x on the top and an x on the bottom. So we can divide those out. So we end up with a 1 here. And this was going to go away too. So that's going to equal the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And then we can use direct substitution, and we end up with 1 over the square root of 0 plus 1 plus 1, which equals 1/2. So notice the important step here was being able to factor the x out of the numerator and denominator after we simplified it. Getting that x out of the denominator was how we kept the denominator from equaling 0. Now we can look at the graph here to reinforce our conclusion that the limit is 1/2. Notice that there's a removable discontinuity at x equals 0, where the point 0, 1/2 would be. But as x approaches 0 from the right and from the left, the limit of the function is 1/2. And we can see that in the table as well. As x is approaching 0 from the left and as x is approaching 0 from the right, notice that f of x is approaching 0.5 from both directions. If we could take a guess at what goes here where the question mark is, we could guess that it's 0.5. And so the limit is 1/2. Now it's time for you to practice your skills using the rationalizing technique. Please pause the video and work on your solution. Once you find your limit, unpause it and see if your solution matches my solution. For this problem, we have the limit as x approaches 0 of the square root of 2 plus x minus the square root of 2 over x. When we try direct substitution, notice that we end up with a 0 in the numerator and in the denominator. So what we want to do is use the rationalizing technique to get rid of the 0 in the denominator. So we're going to multiply both the numerator and denominator by the conjugate of the numerator. So once we distribute the numerators and cancel middle terms, we end up with 2 plus x minus 2 in the numerator. We can cancel out the 2 and negative 2, and then we end up with an x in the numerator, and then we also have a factor of x in the denominator. We can cancel out those factors, and we're left with a 1 on top. And so we have the limit as x approaches 0 of 1 over the square root of 2 plus x plus the square root of 2. Now we can use direct substitution. After we use direct substitution, we end up with 1 over 2 root 2. And then we can rationalize the denominator by multiplying square root of 2 on the top and the bottom. And we end up with square root of 2 over 4. Notice that I wrote down that we're using theorem 1.7 here. That's because we start out with the function f of x equals square root of 2 plus x minus square root of 2 over x. And once we use the rationalizing technique, we end up with the function g of x equals 1 over square root of 2 plus x plus the square root of 2. And these functions are equal to each other except at the point x equals 0. And you can see that pictured here in the graph. We have the graph of f of x. Notice that there's a removable discontinuity at x equals 0, where the point 0 radical 2 over 4 would be. But the function g of x would look exactly the same, except there wouldn't be a hole at that point.
Well, that brings us to the end of this video. Please join me for the last video for section 11.1, Limits that Fail to Exist.